A very good morning to all of you. Today we'll talk about low noise amplifiers. We will see some design aspects and also in cadence virtuoso how to verify the figure of merits. Okay, so this is how and generally an basic low noise amplifier would look like. Low noise amplifiers are employed as a front end for of any RF receiver. Okay, so there will be an antenna which will receive the desired frequency. I need to amplify just the desired frequency. The antenna would pick up a lot of atmospheric noise also, so those should not be amplified. So one of the requirements of the low noise amplifier is to amplify just the required signals. Okay, so there should be some selectivity, okay, of frequency, and here I am using an tank circuit out here. Okay, LC tank circuit which will allow me to select the desired frequency. I have put a resistance out here because any spiral inductor which is implemented in a VLSI chip will have some series resistance. So just to make it a bit more realistic, I have put this resistance. We may want to add higher value of resistance if you want to increase the Q. Okay, so if you refer to my lecture, the first lecture on LC tank circuit, you will get more idea about this. Okay, so this is the tank circuit for selectivity. I have used a cascode structure because this is a CS, this is an transistor in CS configuration, in CG configuration, so that there is no Miller effect out here. Otherwise, the Miller effect will have an enhanced capacitor at the gate of this, and which will deteriorate the high frequency application. So if you want to know about cascode amplifier, you could refer to my lectures on analog IC design. Okay, so these are the two resistors that have been used to bias this particular transistor. Okay, now in many a times you may want to have an LNA which is tunable to different frequency. At different point of time you might want to receive different frequencies and tune it to the corresponding frequency. In that case, instead of having a fixed capacitor, we can have an PMOS here and apply the voltage. So this PMOS varicap tuned amplifier I have again covered in the RF microwave course. Okay, you could have a look at that, or we could even have an active inductor to obtain these kind of selectivity. Okay, with very high Q and low silicon area, because these inductors, they take a lot of silicon area. So this also I have explained in my previous class, so you could have a look. Okay, so but today we are going to analyze with fixed LC, okay, for one particular frequency. You can do the analysis for the other frequencies as well if you are using a tuned circuit. Okay, so what are the figure of merits? Okay, one is the AC gain. Okay, so at the desired frequency should be amplified right, minimum to some level, maybe 5 dB, 10 dB, 15 dB, whatever the case may be. Obviously it should be able to amplify only the required frequency, and the bandwidth is important. Okay, now once we get the AC analysis correct, and the next thing we should see, we should do a transient analysis and verify that the we are getting a correct signal at the output. There is no clipping which can generate higher harmonics. So we should verify that in the transient analysis we are getting the same gain as that of the AC, and there is no distortion there. Okay, so that distortion can be seen in the transient analysis. And then we also have to plot the total noise figure of the circuit. Okay, so the noise factor is defined as signal to ratio at the input and the signal to noise ratio at the output, and obviously the signal to noise ratio at the output will be lesser than the signal to noise ratio at the input. That is because this input signal and the noise are going to get amplified by the same factor G, but the amplifier itself is going to create some noise. Okay, so obviously at the output there is going to be some additional noise. Okay, so that is going to reduce the signal to noise ratio at the output, and hence the noise factor F will be greater than 1 always. Okay, if the amplifier has got zero noise, only then F will be 1. Okay, so it should be as close to 1. Okay, and the noise figure in dB is 10. This is not actually log 10F. This is the base 10. Okay, base 10F. So so that will always be greater than 0 dB, right? So the best case is 0 dB. right? But anything below 3 dB is generally acceptable. Okay, that depends on the user to user requirements. So we will target to keep it below 3 dB. Okay, the other figure of merits is S parameters. Okay, so if this is a two-port network, this is the incident power A1, this is the reflected power A1, and this is the power being given to the load, and this is the reflected power from the load. Then there are 4 parameters. Okay, S11 is network input reflection coefficient. Okay, so if I have S11 very low, it means that all the power which is there here is being transferred into the port network. That means an input impedance of the antenna or a source is perfectly matched with the input impedance of the circuit. Okay, in that case S11 will be very low. Okay, forward gain is nothing but the AC gain. Okay, this is the output reflection and the reverse gain. That means if there is a signal out here noise, how does it appear at the input? Okay, so these two things actually will not discuss much, because for that the output circuit needs to be designed properly. Our focus is on the LNA aspect, so we will talk about these two in details. Okay, so this is like in the initial circuit, and we didn't have these two inductances. Okay, so we can put these two inductances out here, so that the impedance of this particular port, generally an antenna of 50 ohms, and the impedance as seen here into the circuit, okay, this is also 50 ohms. Okay, so that this entire power is transferred to the network. Okay, so by putting these two inductors, okay, the capacitance of this can be cancelled, and then we can have an 50 ohms effective input impedance. Okay, so this is the design steps. Okay, how to choose the value of this resistance and this. So this is listed out here. I'm going to share this PDF in the course page, so you can follow these steps. Okay, so by appropriately choosing these two, selecting these two values of these inductances, depending on the capacitance what we have used here, we can tune this circuit, the input impedance, to around 50 ohms, so that the maximum power transfer can happen. Okay, now let's go to the simulation and see how things work out there. This is the LNA which I have drawn in cadence. I have taken the inductance to be 5 nano Henry and capacitance to be 10 pico. So if you see the LC, it would come around 711 or something. Okay, during the that's the omega is equal to 1 by root LC, right? So that resonant frequency will come around 711 megahertz, something close to that. Some minor capacitances will be contributed by this NMOS also at this node. So the resonant frequency can be plus minus something from that value. Okay, so first let's do an AC analysis. So here I have taken a port, right? This is a sinusoidal port, okay, and 50 ohms, and I have given 724 megahertz, okay, as the input signal. And here again I have put a DC port out there of 50 ohms. Okay, so this is just the load, and this is a source of sinusoidal source with 724 megahertz. Okay, and let's do an AC analysis. So launch AD Explorer. Okay, so let me show outputs to be plotted on the design. Okay, I have taken this output voltage out here. Okay, V out. So V out is being plotted. Analysis. Okay, let me first just show the AC analysis. Okay, choose. So for the AC analysis, okay, I have taken from 1 megahertz to 2 gigahertz, and points per decade is 100 and logarithmic. Okay, so this is the AC analysis setup, and I am running the simulation. So this is the plot I get, right? So if I am just putting a marker out here, so theoretically when we calculated just LC, it was around 711, but then maybe because of the no, additional capacitance being through the PMOS, or this could be right because we are taking some 100 points per decade. You could take further refine it and probably see there could be some minor changes in this, but more or less you are getting 724 in the same range. Okay, theoretically what we got. So that's the AC gain, and I have given a magnitude of 1, and this magnitude is around 16. So that means the signal is being amplified 16 times. Okay, so that's good, right? So we are able to take the particular frequency, and the bandwidth also you could come down to 3 dB from here, 16, right? So you have to plot in dB and put it 3 dB. So for that I think what we can do is right output I think results plot outputs is AC results, and okay, I think results direct or direct plot AC gain and phase. Okay, now you have to first click on the output and then click on the input, right? So in that case you will get in the dB. Okay, so this is in the dB, right? This plot. So if I put a marker out here, so it is no, that's the phase. Sorry, let me remove the phase. This is 20 dB, right? Okay, so mark. So it is giving me around 18 dB gain. Okay, so this is the gain in dBs. Okay, so we can do that. So AC analysis, you can, this is the AC response. So in dB. Okay, magnitude wise also we saw it is coming around 13, I guess, right? So 20 log 13 would maybe come around 18. Okay, so that's in the dB, right? So now we saw the AC analysis. Now see, we every time we do an AC analysis, we can't be sure that just doing AC analysis that the signal is actually amplified here. So we need to do a transient analysis also. So let me stop this AC analysis and do a transient analysis. Okay. So in the transient analysis, let me show what I'm doing is I go choose, okay, in the, let me close this again, I'll run it once again, no problem. In the transient, I am just giving 0.04 micro, and I'm giving it conservative so that more number of points are plotted, and I can see that there are no distortions. I want to confirm that aspect. Okay, and that's the reason I am giving. So that's the transient analysis. So here transient analysis is staked, and I am giving a transient analysis simulation. So this is the plot. So now I can see that there are no distortions, and probably I can again go to the scale, and I can put a manual scale out here, and I can, let me just see 30 nano out here. Okay, I see a perfect sign at the output. There's no distortion. I don't see any distortion out here. Although if you're keen, you can do the 1 dB and 3 dB 1 dB compression point and all, as explained in the previous class. Okay, so now I have to verify the gain. Okay, so I put a marker A there, and I put a marker B there, and I see that it is 356 millivolt, okay, peak to peak. And what's the input voltage I gave? 10 volt peak to peak, no, 10 volt amplitude, so 20 volt peak to peak. And this is 356, right? So you are getting that many times, around 16 times the magnification. So on the transient analysis also I could verify that no, this is working, the circuit is working fine. Okay, so the next analysis which we need to do is the noise. Okay, and to do that we go again to analysis, and we can select the noise out here. Okay, and here noise I am giving from 1 megahertz to 2 gigahertz, okay, logarithmic scale 100. Here we need to set this output noise. Okay, where do I want to see the output noise? Voltage. Okay, so I can select this voltage, and I can go and select this. Okay, I want to see the noise which is there in the output. Okay, so that's output, and with respect to ground. Okay, so I again select the ground here, so it would come here ground, and the port. Okay, what is the input? Where is the input? Okay, with reference to the input, so I can select. Okay, here select. Once I do select, it will come here, so I go to select that. Okay, so the input port, so I have given the name of this input as p underscore in, and this as p underscore out. Okay, for these ports. Okay, here I am just finding out the noise at this particular output voltage level here. So I have given v out here, that's the voltage. You can give a port also there. Okay, you can, from here you could select a port also, right? So this is what the selection for the noise. Okay, and then I do an right, I can alright. So it says I have not done any analysis because, okay, I need to select this noise out here, and then I'm running the simulation. Right, and so this is the noise amplitude. Okay, in v square by hertz. Okay, so you can refer to my lecture on noise. So this is the noise. Okay, so this is the noise amplitude. Okay, and in the AC analysis, if I put a marker out here, so it is in some 10 to the power of minus 15 volts. Okay, so some obviously where this circuit is tuned, okay, in around 707 megahertz, the noise will be more because only that component of the noise will get amplified, rest of the noise will be neglected. So but then it is not amplified as much as the required signal. Okay, so there is small noise which is getting amplified. So this is the internal noise of the circuit. Okay, so this is what it generating very low noise. Okay, so you can see that out here. We can also do results, okay, on direct from main, and we can do the noise figure, right? Okay, noise figure also we can do the plot, right? So this is the noise figure. So if you see here there's a lot of noise here, but at the desired frequency, because at low frequencies the MOSFETs and all, they have because we have used large size MOSFETs, at low frequencies it will have noise. So this is at 189 megahertz, and as you go towards what we have designed this around 724 or right, 724 megahertz. Okay, it is 1.3 7 dB, right? So like we said, below 3 dB is acceptable, right? Ideally it should be 0 dB, but it can't be 0 dB, so 1.3. Now this is the number. So now if you want to know what are the components which are really creating this noise, okay, where is this noise coming from, that also we can do that. We can what we can do is excuse me, we can go to results, and we can say print. Okay, and we can say noise summary. Okay, and at whatever is the desired frequency, say suppose I want at 700 megahertz, at whatever frequency, and then include all types of noise, and then we can say top 10 noise contributors. Okay, I want. So if I do that, So I'll get a report like this. Okay, now if you see the input resistance of 50 ohms, which is there in the input side. Okay, so any noise which is generated by that resistance is going to be amplified by the by the LNA also. So and hence at the output side, that is the one which is causing the maximum noise. But whereas the output port, that doesn't that is also 50 ohms, but that is not being amplified. So you will find that that is causing negligible noise. Correct. The input resistance is the one which is causing more noise, because the that resistance is going to is there in the input side and going to be magnified by okay. And then the input transistor, you go to refer to my lecture on noise, that this transistor has got several noise components: ID noise, and FN noise, flicker noise, thermal noise. So which component is of that MOSFET is contributing what kind of noise, everything, the details can be. Now depending on this analysis, if you find that you need to adjust few things to reduce the noise and things like that, accordingly we can do an analysis and then try to minimize the noise. Okay, so we can't blindly change the we know once you go through the lecture on noise, you will come to know how to reduce these noises. Okay, so most of the noise are inversely proportional to W and L, so you can increase W and L and probably reduce these noises. So obviously there will be area penalty, and the increased capacitance can also affect your frequency, high frequency operation. So all those things can be taken into consideration, and accordingly you can modify your device size. Okay, so this will give the noise summary. Right. So the next analysis what we can do is the SP. Okay, S parameter. Okay, that's S parameter. For that again you can go to analysis, and you can choose, and you have something known as SP out here. Here it is important that we have to select the ports. Okay, if you go to select, first you need to select the input port and then the output port. Okay, this order is very important. Okay, we can't select the output port first and then the input port. Okay, first input and then output, because S parameters, and for doing the S parameters, okay, the these things have to be clearly specified, right? The input port and so if you see here, input port and then the output port. Okay, and this frequency is same, like 1 megahertz to 2 gigahertz points per this logarithmic scale, and 100. Okay, so I can do that, and then I go back here, right? And now let me SP is selected out here, and I'm doing an analysis. So analysis is done. Then again I go to results. Okay, direct plot, main form. Right now here SP is selected. Now what do I want? Okay, now if I let me plot S11, right? So this is the previous one. So let me just delete that. This is the S11 plot. Okay, that is the input reflection. Now if you see here, the input reflection is not that very good. It's around 0 and all, because we have not put those two inductors at the input. We will see that. Okay, how to improve. So S11 is bad, whereas if you see S21, right, this is the gain. Okay, we said S21 is nothing but the gain of the amplifier. Okay, so that is okay. I can plot an other parameters also, right? These are the other parameters also which I have plotted. So, but actually the other parameters are more pertaining. It will be, we actually have to look that only once we design the output stage also properly. Okay, as of now we will focus only on the S21, which is the forward gain, which I am getting it properly, and S11 I am not getting a good value out here. Okay, that I have not, because I have not done any input matching at all here. Okay, so now let me try and do that. Let me modify this circuit, and then see what happens. So here I have just put two resistances out here, okay, two inductances, so that the input matching is done and my H11 parameter is better, okay. So right, so here if you see here, I'm going to plot S11 out here, okay, and if you see, let me do just the S parameter analysis. I have placed in two inductors. One is 0.185 micro and 0.185 micro. L1, L2. I have kept it as variable out here, right? Both these inductors I have L1 and L2. I have kept it as variables. So and I have given a fixed value of 0.185 micro and 0.185 micro microhenry, right? So if I do the simulations, see now if you see here, this is the S11 parameter. So at the desired frequency, right? So I can tune that, okay? So I can 707 megahertz, okay? There is those two inductors in conjunction with the MOS capacitance, okay, gate capacitance of the bottom transistor, they form a perfect matching at that particular frequency, right? And there's very less input reflection that if you see here, it is going to minus 16 dB or something, right, like that, right? So if you see here, minus 17 dB, that means the input signal, the total power of the input signal is being reflected onto the MOS transistor for so there is a perfect match here. So the input, so now what I have done from the previous circuit, if I go here, so what I have done is I have inserted these two and ensured that this maximum power transfer condition is met. So that maximum power from here is transferred here, and hence very less reflection is happening out here, okay. Now when you put these two, you got to be careful that there could be some loss of gain happening here, right? So then again, this is all a bit complex design, like if you try to optimize one thing, the other can get deteriorated, so you got to re-verify again whether by adjusting these has something deteriorated. So if so, then again you might want to adjust the parameters of these MOS transistors and all to get back the desired. Most likely the gain might have got deteriorated because this is a source degeneration thing available out here, right? So this can result in a little bit of drop in gain. So accordingly, if you want to again get back the gain, probably you can consume more power out here and increase the GM of these two transistors, and or use higher length of transistors and increase R0 and whatever. So that thing needs to be analyzed properly, okay. So with this we'll end it up here. In the next class, probably if I get time, I would be talking about mixers, how to design mixers and do the analysis. Thanks a lot.